Mark this date on your calendar, December 2026. It is not the date of a manned mission to Mars. It is not the return of a comet. It is the moment humanity receives a verdict we have been waiting for since we first looked up at the stars. For decades, we have been haunted by a single, terrifying statistic. We have found over 5,000 planets orbiting other stars. We have found super-Earths, mini-Neptunes, and hot Jupiters. We have found worlds where it rains glass and worlds made of diamond. But do you know what we haven't found? Not even once. Another us. Another solar system like ours. In late 2026, a spacecraft named Gaia will release its fourth massive data dump, Data Release 4. It contains the hidden motions of over 1 billion stars. And hidden within that data is the answer to the ultimate question. Are we a freak accident of the cosmos, or are we just blind? The answer will either ignite a new era of exploration, or confirm our deepest fear, that we are truly, terrifyingly alone. To understand why 2026 is so critical, we have to understand how spectacularly we have failed at finding ourselves. The story starts in 1992, not with a sun-like star, but with a corpse. Radio astronomers detected the first exoplanets orbiting a millisecond pulsar, a dead star spinning 160 times a second, blasting its surroundings with lethal radiation. It was a monumental discovery, yes, but looking for life there would be like looking for a picnic spot inside a nuclear reactor. It wasn't home. Then came the Doppler era. We watched stars wobble. We found gas giants, monsters scorching themselves close to their stars. Again, impressive, but nothing like home. Then, in 2009, we launched our greatest hope. Kepler was a numbers game. It stared unblinkingly at 150,000 stars, waiting for a planet to pass in front of them, a transit. And it worked. The floodgates opened. Suddenly, we knew of thousands of worlds. Statisticians crunched the numbers and told us something optimistic. There could be 11 billion Earth-like planets in the Milky Way alone. 11 billion sounds like a lot. It sounds like the galaxy should be teeming with Star Wars-style civilizations. But there was a catch, a massive, glaring anomaly that no one talks about enough. When we looked at the architecture of these thousands of new systems, they looked wrong. In our solar system, we have a clear structure. Small rocky worlds on the inside. An asteroid belt. Then, the gas giants Jupiter and Saturn protecting the outer rim. It's organized. It's stable. But the systems Kepler found? They follow a pattern astronomers call peas in a pod. Imagine a system where you have 5, 6, or 7 planets packed tightly around their star, all roughly the same size, usually super-Earths or mini-Neptunes. No gas giants in the back, no rocky dwarfs in the front, just uniformity. It turns out, the standard mode of planet formation in the galaxy produces these cramped, uniform systems. They are the rule. We are the exception. And this leads to the grand tack hypothesis, the idea that our solar system is the result of a violent, unique history. Some theories suggest that Jupiter didn't just stay put. Early in our history, it migrated inward, like a wrecking ball, clearing out debris and starving the inner planets of material, preventing them from becoming those ubiquitous super-Earths. Then, pulled back by Saturn, it settled into the cold outer reaches. This cosmic dance might be the only reason Earth exists as a small, habitable rock. Jupiter acted as both a destroyer and a shield, deflecting comets that could have wiped us out, while allowing us to form in peace. So, here is the billion-dollar question. To find another Earth, We shouldn't be looking for Earths. We should be looking for Jupiters. We need to find a system with a cold, distant gas giant acting as a bodyguard, and surely, with 5,000 planets confirmed, we've found plenty of those, right? 0. Confirmed Sun-like stars with an Earth-like planet and a distant Jupiter-like companion? 0. Is it because they don't exist? Or is it because our technology is fundamentally broken? The answer lies in a blind spot that has plagued astronomy for 30 years. A blind spot that only one machine can fix. And in December 2026, that machine speaks. So, why have we failed to find the Jupiters that might be protecting other Earths? The answer is frustratingly simple: time. Remember how Kepler works. It watches a star and waits for it to blink. To confirm a planet exists, science requires rigor. We need to see that blink, not once, not twice, but at least 3 times to establish a pattern. If you are an alien looking at our sun, waiting for Jupiter to transit, you have to wait 12 years for the first blink, then another 12 years for the second, and another 12 for the third. That's 36 years of staring at the sun without blinking. Kepler only watched the sky for 4 years. It never stood a chance. It was physically impossible for our best telescope to find our solar system's most important protector. But it gets worse. The transit method has a fatal flaw: geometry. It only works if the star system is perfectly aligned with us, edge on. If a solar system is tilted even slightly face-on to Earth, the planets will never cross in front of the star. They are invisible to Kepler. They are invisible to TESS. But wait, you say. What about the wobble method? The Doppler effect? True. The radial velocity method doesn't need a transit. It measures the star getting pulled back and forth by gravity. But there's a catch. Doppler is fantastic at finding heavy planets close to their stars, where the gravity is strong and the wobble is fast. But a distant Jupiter? The pull is weak. The wobble is slow. Trying to find a Jupiter using Doppler is like trying to feel the gravitational pull of a mosquito flying around your head from a mile away. So here is the terrifying reality. For 30 years, we have been taking a census of the galaxy, but we've been using a camera that can only see the short and the close, the wide and the distant. The very architecture that makes a solar system habitable has been hiding in the lava. Dark. Until now. To solve a 21st century problem, we are going back to a 19th century idea. In 1844, astronomers looked at Sirius, the brightest star in the sky. They didn't have spectrometers. They didn't have light curves. They just had position. They noticed Sirius wasn't moving in a straight line. It was wiggling, spiraling, as if it was dancing with an invisible partner. That ghost turned out to be Sirius B, a faint white dwarf star. They found it using astrometry, the science of measuring exactly where things are. Here is the physics that changes everything. Planets don't orbit stars. They orbit their mutual center of mass, called the barycenter. When a planet is close to the star barely moves. But move that planet out, make its orbit wide, like Jupiter, and leverage takes over. Paradoxically, the further a planet is from its star, the more it makes the star physically move in a circle across the sky. This is the opposite of the Doppler method. Doppler loves close planets. Astrometry loves distant giants. Astrometry is the Jupiter hunter we have been waiting for. But there was a problem. The wiggle caused by a planet is microscopic. To see a Jupiter-sized wobble from Earth is like trying to spot a coin on the surface of the Moon. Enter Gaia. Launched in 2013, this European spacecraft is a masterpiece of engineering. It doesn't just stare at one patch of sky like Kepler. It spins, scanning the entire celestial sphere, over and over again. By cross-referencing observations over 10 years, Gaia can track the tiny, looping paths of over 1 billion stars. It ignores the blink, it ignores the speed, it watches the dance. And unlike Kepler, it doesn't care if the system is edge-on or face-on. It sees everything. For the last decade, Gaia has been silently collecting this movement data, and in the preliminary releases, we got a glimpse of what's coming, and what we saw was strange. We don't have to wait entirely until 2026 to know if this works. Gaia has already given us a teaser in its Data Release 3, and it found something monstrous. Meet Gaia 4b and Gaia 5b. These aren't just planets, they are super-Jupiters. Gaia 5b is 21 times the mass of our own Jupiter. But here is the shocker. They are orbiting small, low-mass stars. According to our old theories, small stars shouldn't have giant planets. It's like finding a blue whale inside a goldfish bowl. It was thought to be extremely rare. But Gaia found them, and it found them exactly where the other methods failed, on wide, distant orbits. This is the smoking gun. It proves that the wobble method works for distant giants. It proves that there is a hidden population of planets out there that we have never seen before. Gaia 4b and 5b are just the tip of the iceberg, the scouts before the invasion. Which brings us back to December 2026. Data Release 4. This release will include 5.5 years of observation data, twice as long as the previous set. That is the magic number needed to confirm the orbits of Jupiter analogues. Astrophysicists Caleb Lammers and Josh Wynn have run the simulations. They predict that this single data drop will reveal approximately 7,500 new exoplanets. That number alone doubles everything we've discovered in the last 30 years. But wait, look at the prediction for the final release in the 2030 seconds. 120,000 planets. We are about to go from a scarcity of data to an absolute flood. And this is how we solve the puzzle. TESS watches the inner system. Gaia watches the outer system. By overlaying their maps, for the first time in history, we will see the whole picture. We will finally spot the systems that look like us. A rocky Earth, protected by a distant Jupiter. So, what happens in 2026? There are two possibilities. Possibility 1. We find thousands of solar system twins. We find that our architecture is common, that Jupiters are everywhere, shielding Earths everywhere. If so, the galaxy is likely teeming with life, waiting for us to say hello. Or, Possibility 2. The data comes back silent. We find thousands of freaks, thousands of peas in a pod, but no one like us. It would confirm the rare Earth hypothesis. It would mean that the chaotic dance of Jupiter that formed our world was a 1 in a billion miracle. If that is true, if we are that rare, then the silence of the universe is not empty. It is heavy. It means we are the only candle flickering in the dark. And it is our duty, our only duty, to make sure that flame never goes out. In 2026, we find out.